right, it's my pleasure to speak to DCHPC 2024 participants, which include a number of my former colleagues and quite a few of my students, as I understand. So my topic is fixed degree and constant diameter interconnection networks for parallel supercomputing. Interconnection networks is one of my main areas of research, but I'm going to focus today on a particular aspect of interconnection networks, as I will define it. So these are some of the topics that I'll touch upon. This is not an outline in the sense of me going through things sequentially, but these are the topics. I'll talk about graph theory, the degree diameter or DD problem, a little bit about types of networks, performance attributes of networks. Then I'll define the class of constant diameter networks and give you a few examples, and the class of fixed degree networks and give you a few examples, and then summarize and conclude and answer questions if there are any. Now, a parallel computer consists of nodes and interconnects. Data center networks also consist of servers and interconnects. So there's a lot of commonality between parallel computer interconnection networks and data center interconnection networks. In fact, fundamentally, the internet is also the same. It's a bunch of nodes and interconnects. And networks on chip are also the same, have the same elements. But for both network on chip and the internet, the balance point or the design trade-offs are substantially different. Whereas for parallel processing interconnection networks and data server networks, the issues that we are interested in are kind of similar. So here is an example of a network. It's a toy example, very small. Nodes are numbered, 0 through 9. Links connect these nodes, and we define the distance between nodes as the number of hops. So in going from node 0 to node 9, the shortest path goes from 0 to 1, 1 to 5, and 5 to 9, we have 3 hops. In going from node 3 to 6, we also have 3 hops, hop 1, hop 2, hop 3. And in fact, the diameter of this network is 3. In other words, there is no distance in this network that is greater than 3. Node degree varies from 3 for this node to 6 for this node. Now, typically, interconnection networks that we are interested in for parallel processing are regular. They have uniform node degree, and that regularity or uniformity, symmetry, so to speak, is a very important attribute that simplifies a bunch of things, including routing algorithms and other things that we are interested in. So let me go over the degree diameter problem. Lowercase d is the node degree of networks. Uppercase d is the diameter. This is a classical problem in mathematics and graph theory that remains unsolved in its full, most general form. So here I've shown a bunch of nodes at the upper left of my slide. All of them are of degree 4. And I want to interconnect them into a network for parallel processing. And this can be done in a number of ways, many different ways. And I've shown some examples here. I can interconnect them as a mesh, 2-dimensional mesh, shown here, bottom center of the slide. 2-dimensional torus, bottom right of the slide. Binary tree, top right, or some ad hoc acyclic network. Now these are all of these architectures use the same degree 4 nodes, but they have different attributes, different parameters. So they are different with respect to performance parameters. So here are some examples of those performance parameters. The diameter is 4 for this network, 4 for this mesh, 2 for this torus, and 5 for this binary tree. And the shorter the diameter, the higher the communication performance, the lower the latency of communication in the worst case. The bisection width ranges from 2 for this network, 4 for the mesh, 8 for the torus, and 1 for the tree. When the bisection is small, in other words, I can just cut one link and bisect or divide this network in 2 parts. It's a sign of low resilience. In other words, a single edge or link failure, this one, can disconnect part of the system from the other part, and that's not a good attribute. Whereas when the bisection is large, it's much harder to cut the network in 2. On the other hand, with respect to packaging, which is one of the considerations in building networks, a small bisection can be helpful because if this network does not fit on a single chip and I have to use 2 chips, then I can cut the network through here, put the right half on one chip and the left half on another chip, and the 2 chips will be connected by just one wire, one line, one channel. So I'm giving you these examples to tell you that there's a lot of trade-offs between these parameters. Large bisection width is good for the bandwidth of communication. Small bisection width make it easier to partition and package the network. And we have to sort of balance these 2 requirements in order to build practical communication network. Now today, I'm going to ignore for the most part, given the limited time, all these various practical things like partitioning of networks, VLSI layout, wire length, robustness, and just focus on topology. In other words, how to connect nodes so that from a graph theoretic point of view, we have desirable properties for these networks. Now, diameter is sometimes criticized. I'm someone who pays a lot of attention to diameter and consider the diameter of a network to be important, but others sort of discount the importance of diameters because they say that just as in algorithm analysis, we have stopped worrying about just the worst case performance, and we are paying more attention to average case performance. In networks also, we have to stop worrying about the worst case distance, which is the diameter, and pay more attention to the average internode distance, which is more indicative of the expected performance of the network. So worst case can occur, but it's not very common, therefore we should not worry about it. So they are saying that diameter, we should ignore diameter and focus on average internode distance. However, for the networks that we use in parallel processing and are usually symmetric, this theorem I proved many years ago, that the average internode distance, of course, is less than diameter. Diameter is the worst case distance. So the average is obviously less than the diameter. But also greater than half of the diameter. This is provable. It's just a theoretical result. And therefore, you can't simply dismiss diameter because average internode distance is very related to the diameter. If you have the diameter, you sort of have an idea of what the average internode, the range of the average internode distance. So with this in mind, I'm going to continue paying attention to diameter. So here is the degree diameter problem. Suppose you have an unlimited supply of degree D nodes. How many can be connected into a network of diameter D? In other words, with a given diameter, we want to maximize the number of nodes in the network. And these are some examples of networks that actually accomplish this. The 10-node Peterson graph, these are two drawings of the Peterson graph, maximizes the number of nodes with diameter 2, node degree 3. Node degree is always 3, diameter is 2, and it's impossible to have more than 10 nodes in such a network. And the Hoffman-Singleton graph, this one, it's a little bit more complicated. It has 50 nodes, the diameter is equal to 2, and node degree is equal to 7. But these graphs such as this that maximize the number of nodes are relatively rare. And for many node degrees and diameters, we do not have an optimal network such as these two. And the best we can do is to try to approach what is known as Moore bound. So Moore bound says, if I have degree 4 nodes, then here's one of the nodes. That node has 4 neighbors. That's degree 4. So there are 4 neighbors. Each of those 4 neighbors will have 3 more neighbors because the degree should be 4. One of the links is already used here. There are 3 more. So that gives us 12 more nodes. Each of these will have 3 neighbors, 36 nodes here. And each of these will have 3 neighbors, 108 nodes at this level. So if I want to limit the diameter to 1, 2, 3, 4, the number of nodes in the network cannot exceed the sum of 108, 36, 12, 4, and 1, which is 161. This is known as Moore bound for undirected graph. There's a corresponding bound also for directed graphs. But for undirected graphs, Moore bound said basically, what is the maximum number? And here, of course, I'm assuming that these nodes, there's no repetition. In other words, none of these nodes at this level is the same as the node at this level. If all of these nodes are distinct, then the number of nodes that I can accommodate with diameter 4 is 161. And as I mentioned, for many degree diameter pairs, we don't know how to construct networks that achieve this bound. And in fact, it may be impossible to achieve it. So we try to get close to this bound, synthesize networks that come close to achieving Moore's bound. And those networks are good enough for practical applications. So these are the really very rough charts that I've shown here. Take it with a grain of salt. If you have diameter that varies, so diameter is your independent variable, node degree as a function of diameter, so diameter is a constant given to you, let's say 15, node degree as a function of diameter is specified by this function, the dth root of n. So as I'm willing to increase the diameter, I can use nodes of smaller and smaller degrees. The green line is diameter as a function of node degree. So if I'm willing to use nodes of degrees, higher and higher degrees, then I can reduce the diameter according to the function log base d of n. Okay, so for a given fixed degree, the diameter, the best diameter that I can achieve is log base d of n, or I should say order log base d of n, there will be a constant in front of here. And for a given diameter, the best node degree that I can achieve is proportional to the dth root of the number of nodes n. Okay, here I've shown the degree and diameter spectrums. The diameter 1 belongs to the complete network, shown here. Diameter 2, perfect difference network. This is a network we invented at UCSB. And as you increase the diameter, you get to torus, ring, linear array on the other extreme. Similarly, for node degree, of course, node degree 1 doesn't make sense because you cannot connect many nodes with node degree 1. Starting with 2, node degree 2, you can build linear array or ring. As you increase the node degree, you can build more connected networks. At the extreme, with n-1 connections, meaning every node connected to every other node, you have the complete network. So when I talk about constant diameter, I'm talking about this end of this spectrum, small diameters. And when I talk about constant or fixed node degree, I'm talking about this end of this spectrum. Okay, these will make more sense as I give you some example. So here is an example of a diameter 1 network on the left side of the slide. This is a complete graph, K9, complete graph with 9 nodes. Every node is connected to every other node, so diameter is 1. Okay, of course, once the size of this network grows beyond maybe 100, 200, then it becomes impractical. If you have 200 nodes, every node must be connected to 199 other nodes. So there will be just too many connections. So practically speaking, this is not a good interconnection network. If you use a bipartite complete graph, then you can reduce the node degree a little bit. So this is a 10 node bipartite graph. A node degree is only 5 instead of being 9. Okay, but still not very practical. Okay, before I introduce the perfect difference network, let me show you corridor ring networks. A corridor ring network is a network that has a ring, okay? At the basis of it is a ring. And then there are these chords. Chords are basically connections between nodes that are not adjacent on the ring. So in this particular ring, I have the ring connections, 1 to 2, 2 to 3, 3 to 4, and so on. I also have chords, 1 connected to 6, 3 connected to 8. So 1 plus 5 is 6, 3 plus 5 is 8. So the rule is sort of like that. This is a unidirectional corridor ring network with 8 nodes. This is the perfect difference network. So in this case, each node is connected to the next node, to the previous node, to node that is 3 ahead, 1, 2, 3, this one, and to the node that is 3 back in the other direction, 1, 2, 3. So each node has 4 connections, that's degree 4, -1, +1, -3, +3. So why is this network important? Perfect difference sets have been discovered a long time ago by mathematicians. So for example, that network that I showed you is based on this set, 0, 1, 3. So 0 is you can just ignore because each node is connected to itself. Each node is connected to, if it's I plus 1, to I plus 3, I minus 1, and I minus 3. And every node can be reached from any other node in 2 steps. Because the property of the perfect difference set is that any number in the range of numbers that are nodes is the difference of 2 of these numbers. Okay, let me go to the second set. So 1 is 1 minus 0. 2 is 3 minus 1. 3 is 3 minus 0. 4, let me see. 4 is, in terms of difference, yeah, so this network has 13 nodes, and therefore arithmetic is done modulo 13. So if I want to construct a path to node number 4, I can go to, oh, sorry, I don't remember that. But this is a property of a perfect difference set. Perfect difference set is a set so that any number in the range, in this case 0 to 12, nodes are numbered 0 to 12, can be synthesized by the difference of 2 numbers. Okay? And then as I want to build larger networks, I have to get these larger perfect difference sets. So perfect difference networks have a diameter 2, and we know how to synthesize these perfect difference sets that allow us to build such networks. Okay, another concept that we need in the subsequent slides is the concept of product and power networks. The product of 2 graphs is defined as another graph, which has the number of nodes is the product of the number of nodes, and the connectivity is defined as shown here. And this is a power network. This network to the power 2 or multiplied by itself is this network. Okay, so power network is the product of identical networks. Okay, now I showed you here that I can build a network of diameter 2. The problem is that this network, the node degree grows as square root of n. In other words, if I want to have 1,000,000 nodes in my network, which is nowadays very common in high performance parallel computers, square root of 1,000,000 is 1,000, 2 times 1,000 is 2,000. I still require nodes of very high degree, which may not be practical. So the question is, can I build networks of diameter 3, networks of diameter 4? Okay, so if I go back to that chart that I showed you, okay, as the diameter grows, I can use nodes of smaller and smaller degrees that may become practical. So that's the idea. Well, for many years, I've been looking for mathematical structures like perfect difference sets that you can apply to building networks of diameter 3, diameter 4. Unfortunately, I have not yet succeeded in finding these structures. However, I have a method to build networks of diameter 4 by multiplying by the product of 2 perfect difference networks. So here I've taken a 7-node perfect difference network